Hi, in this video we're going to look at controller design. So at the start of the video, we're going to look what actually controller is about, and we're going to look at controller design from the perspective of a root locus. So we're going to use a root locus as a basis for designing a controller. So once we've discussed what actually controller does, we're going to look at different types of controllers, namely the PI controller, the PD controller, and the PID controller. And these three controllers here are actually active controllers. We're going to look at as well as a passive counterparts, one of the lag compensators, the lead compensator, and the lag lead compensator. Let's get started. So we've seen already that the root locus can be sketched to get a general idea of the changes in transient response generated by changes in game. So basically we've seen the root locus are the location of the poles as you start varying the gain of the system. So we've seen the root locus typically allows to choose a proper gain to meet the transient response specification. We've seen before that the location of a pose would have a direct implication on the transient response we get. And remember, we covered all these topics in the chapter on second order systems, where we looked at parameters for transient response like the rise time, like the settling time, like the peak time, percentage overshoot, damping ratio, natural frequency. So all these things we've seen are related to the location of a pose in the complex plane. We'll do a small recap of that in a later slide. So basically setting the gain at a particular value is transient response dictated by the pose at that point in the root locus. So the way we have discussed root locus means as you're varying your gain, you are traversing some paths on the complex plane. So these are different points means you can set the particular point your system is operating at by choosing a particular gain k. Thus, possible responses are limited to those that exist along the root locus. So what we're seeing here is if you had a root locus, for example, as follows, an arbitrary system. So all the locations along these poles here are achievable by varying in k. This is what we've seen. But what if you wanted to get a point A? That's fine because point A is located along the root locus. So you could very well find this damping ratio line here and then see the point of intersection of this damping ratio line with your root locus. You can find this gain k, you set it on your system, and you should be operating at this point. Remember, this point here would have a particular imaginary value, and which is referred to as this one as a depth natural frequency, and this one as exponential dB frequency. And these two parameters here would have an implication. This one we've said to have an implication on the settling time and on the peak time. So we look at equations how to define these two parameters, and also once you set your damping ratio, we know we are also setting our percentage overshoot. So these three parameters here, your percentage overshoot, your peak time, and your settling time are actually transient response specifications. And if you want to have a certain value, it means you can very well decide a gain on the root locus. Now, what if you wanted to have, in this case, a point B? You wanted your system to go through point B here, means you would definitely want to have a different transient response in terms of a lower peak time and a lower settling time, but with the same percentage overshoot. Okay. The desired transient response defined by the percentage overshoot and settling time TS is represented by point B here, which is not part of a root locus. So if you get any point which is not part of a root locus, means whatever gain you choose here, you can never achieve this point. So this is where control design sets in. Your controller would allow you. So you're adding another block in your control system to allow your root locus to actually go through this point. So we look at that different responses we can get for second order systems. As you vary your damping ratio here, you get different responses. Remember, if you get a damping ratio of 0, which is not shown here, you get actually an undamped response. As you start increasing your damping ratio, you start getting lower and lower percentage overshoot, and at some point when you exceed 0.8 or 0.9, and then when you come to 1, you're actually in the critical damping zone where you don't get any oscillation at all. You get the fastest response you can get without any oscillation. If you exceed the damping ratio of 1, now you go to over damp region where you get now a slower response. Okay, so these are the definitions of the transient parameters we've seen earlier. So this is the definition of peak time. So it's a point at which your response. So again, you are considering a second order system, like we're saying. So in a second order system, you can have oscillation and depending on what the nature of your poles that you have. So this is the definition of a rise time here, the time it takes to go from 0.1 to 0.9 of a final value. Then you have peak time, the time at which you get the maximum value, and settling time, we've seen you have a certain criteria attached here. So in this case, it's a 2% criteria. So it's the settling time, we say, is the time it takes the system to reach, but stay within 2% of its final value. Okay. So we derive all this expression in an earlier chapter where you can find your peak time, your percentage overshoot, your damping ratio, okay, and your settling time can all be found here. So these two parameters, we're going to look at these two specifically. This one as well is related to your damping ratio. See, you can see here. So once you set your damping ratio line, you can very well find your percentage overshoot because you find your percentage overshoot is not dependent on the natural frequency, whereas these two are actually dependent. So if you set a given point here on your locus, this is what we mentioned earlier. So you have imaginary value here, and you have a real part. So the real part here is called the exponential decay frequency, and the imaginary value here is called the depth natural frequency. So if you look at the terms for TP, for example, you find TP is equal to pi over this value. So if you take pi divided by this value, you get your TP. Your TS is actually 4 here, so it's a mistake. So actually your TS, so whatever value you're choosing here for your sigma d here, which is of course related to the location report, you just take 4 divided by this value, you get your settling time. So again, clear, you're saying the location of pole at which you're operating is defining your peak time and your settling time. Like I said earlier, this angle here, which is set depending on the line you're setting, you are deciding this damping ratio line. So you're deciding where your damping ratio line, which sets your percentage overshoot, and the particular point you are intersecting your root locus at is going to set your peak time and your settling time. Okay. So this is one simple example here, which can work up if you are given -3 plus J7 for a second order system. You can very easily work out your damping ratio. So if you know this angle here, you can use trigonometry, tan inverse of 7 over 3, and then you can find your natural frequency, which is nothing but the length of this line here. Okay, then you can find your peak time. Your peak time, you see it's simply pi over 7 here, because your depth natural frequency is 7, and your settling time is 4 over sigma d. So your sigma d in this case is 3, so it's going to be 4 over 3. So very simple calculations here, and like I said earlier, it's a basic graphical method here. We can very quickly calculate these transient response parameters. So if you want to compare what type of responses we'll get for point A and B are shown here. So one thing you can easily say here is your percentage overshoot has to be the same because you're having the same damping ratio. In terms of, let's look first at peak time. So peak time we said is pi over this value here. So you can clearly see here the imaginary part is higher for point B. So you expect the peak time to be less for point B. Similarly, to find a settling time for for any of these 2 points, we take 4 divided by the real value. So again, the real value for point B is less. So you expect the settling time for B to be less. If you plot the response, step response for both of these 2 points here, for these 2 locations of poles, this is what we're getting. Like we said, they have the same overshoot, but pole B here would be having a lower peak time and a lower settling time. As you can see, it's settling down quicker as compared to pole. Okay, so you should be able to make this type of analysis on your locus. So the question we can ask ourselves here, why we don't change the system itself to yield a point at B here? So we are currently at point A, so you can very well now just buy a new system which have the which gives you the ability to reach point B here by just changing the game. Yeah, so this is possible. I'm saying not, but the issue is it's quite costly to change the system. So imagine you have a plant and you want to change the whole plant. It's quite costly. But this replacement is expensive and as well as counterproductive. So you might need to stop production and make changes to your production line. Those in the field of production would very well know that this is not very easy to do, and actually it's inconceivable. So in this case, a more effective, a more practical, a more cost-effective alternative would be to actually fit a controller to existing system that you have, to make this change, to allow this board to be selected that won't be here. This is what is control design about. It's not about change the whole plant. That's not control design. It's about fitting system, electronic system in front of your plant to allow adjustment of board to reach the desired location, which cannot currently be achieved just by changing the game. So another term used for controller is to compensate. So you want to compensate the existing system. So we'll talk about the term compensate as well later as an alternative term for controller. So it is a possible disadvantage of compensating a system with additional open loop poles and zeros, increasing system order. So if you start adding poles and zeros, which is what we do in control design, there's the possibility of system becoming unstable because of additional poles. So increased complexity as well. This is one disadvantage. Okay, but we're going to look at that through a simulation of your proposed control design. You have to simulate to see actually what type of response are you getting, because one important assumption you're making here, if you consider the parameters like percentage overshoot, settling time, peak time, or natural response, are all related to second order systems. But it will happen that we have systems of fourth order, fifth orders, but we still be applying these parameters, overshoot, settling time, and peak time. It means you're making here an approximation. So it's very important to, when you have designed your controller, to actually do a simulation to see was that second order approximation valid or not. If not, then you might need to modify your controller further. So what I'm saying is actual transient response obtained by after designing your controller needs to be validated by simulation to check whether the approximation is made proper. So again, that approximation is second order approximation. For example, if your actual system order is 5, now you're going for maybe second order. So it's an approximation which you want to validate. Now there are two main approaches you can use to compensate for a system. One is to introduce a differentiator. This is why we call the T part. So we initially on the title slide here, we have a PD control, for example. So D stands for the differentiator. So when you do differentiation, so you are responding to the transient part, because when you differentiate a signal which is changing, then you are looking at the transient part. Whereas when you integrate, which is the I part, for example, in PI, the I part is integration. So when you do an integration, you actually looking at errors. So you want to reduce error in the system. So when we were discussing in previous chapters, we had one section we look at transient response, which we just looked at. There was another chapter we look at steady state error. So if you want to modify a steady state error, possibly because it's not equal to 0 yet, then you're looking at integration. You would add an integrator. So if, for example, a PI controller, the P part is a proportional part. Proportional part is your gain. So you're always playing around with your gain. Fine, that's the proportional part. But if you want to correct for a steady state error, then you're going to use an integrator part. Integral part. So a PI controller would do that. If you wanted to modify your transient, so you're not happy with your peak time, settling time, or any other parameter, even your overshoot, if you're interested with, you're not happy with it, so you could modify that using a PD controller. If you wanted now to compensate both for steady state error and for your transient, then you have a PID controller. So it makes sense. We're going to come back again to these terms later. This is what we just said here, and the method we're using now is design, or for control design via the root locus method. There are other methods you can use to design controllers, but we've studied very well what a root locus. I hope you are very conversant now with sketching and refining root locus. So we are doing control design via the root locus method, which is a very common method. Right? So 2 ways you can go ahead to do a control design. There is your plant, and this is your original controller. Now you want to do, you can put your controller here as a cascade compensator. So it is in series with your plants, or it could even be as a feedback compensator. So both of these are going to introduce additional poles and zeros, as we've seen when we were working with root locus. Okay, so we have two main methods. We're going to look at the cascade compensation method. So two ways to improve a steady state error of a feedback control system we discuss using cascade compensation. So the first technique we're to discuss now in this part of the video is known as a PI controller. So by adding a pure integrator. Yeah, so pure integrator is nothing but pole at the origin, because we know integration relates to dividing by S. Now, the second method we'll be looking at later is actually not using a pure integrator. A pure integrator actually is an active component which will require a power supply and active components, whereas you can actually go for passive compensators, but we'll see what are the implications later. This is sort of a summary here of everything I've said, so let's read through that. System that feed the error forward to plant are called proportional control systems. This is a gain, if you want, plus the K part, so it's called a P controller. So we already used that when we're doing the root locus. System that feed the integral of error forward to plant are called integral control systems. So these things we've said, the integral of error is going to deal with the steady state error. Systems that feed the derivative of error to plant are called derivative control systems. So it's a P, the D part, and this is going to look at the transient response of a system. So when we look at the first type of controller is a PI controller. So if we're adding here we're adding an integral part through the pole at the origin, so we call it proportional plus integral controller, because we of course have a gain part. So we have the P part is a gain part, and the I part here is integral, which is actually the pole at the origin. So we'll look at this one later, the lag compensator, which is another method which can be used to deal with steady state error. Let's first look at the idle integral compensator, which is a PI controller. So this is how this K here is the proportional part. The S now in the denominator is actually a pole at origin. Now we've seen in the chapter where occurring steady state error, if you have an S in the denominator, you're basically increasing the type of a system. So by increasing the type of a system, you are allowing the system to be able to reduce steady state error. So if you, for example, find Kp or Kv or Ka, depending on the signal you're using, it's clear here as you increase the type of a system by introducing this pole at the origin, you are reducing the steady state error. So let's see how it's done. So consider a system with a root locus as shown below. So brings a new root locus, you can open the poles placed at origin. So let's just study here this particular root locus here. So you would definitely have, in this case, you have 3 open loop poles without any zeros. So by applying the rules for root locus, we know very well that this part of a real axis would form part of root locus, and this part as well, this part would not form part of a root locus. And then, so it basically, this pole here is going to 0 at the, is going along the real axis to 0 at infinity, and these two here would have a breakaway point, and they would go to respective through the respective paths to as well to zeros at infinity. So if currently you're operating at point A here, you're currently operating at point A here, but let's say for this part of the system, you're not very happy with your steady state error, so you wanted to actually introduce here a pole at the origin. Like we said, when you introduce a pole at the origin, you're increasing the type of a system, so you are in a way allowing the system to deal better with steady state error. We've seen that in the chapter on steady state error. Just give you a simple example. If you have, for example, a type 0 system and you are trying to control position here, we said normally you would have non-zero steady state error, so your Kp would be finite. So you have a steady state error which is finite, not 0. But if you had a type 1 system, so if in this case here your system type is type 0, and then you add an integrator here, means you are increasing system type to 1. The type 1 system is able to track position. So if you do that, your system would now be able to track position with a 0 steady state error. So this is basically what we're doing. So what would happen now if you put a pole here? So the first implication, the next slide actually shows the actual root locus you're getting, but just to predict what's happening here, so you'd have this path now is going to form part of root locus. Imagine you have already a pole here, so this is going to form part of the root locus now. This one would not form part of a root locus. and this one would form part of root locus. Now it means now you have four branches because you have four poles, and all you have two breakaway points now, one breakaway point on this one, so you have two paths, and as well as this part here, because this is going to form part of root locus. So again, you will have these two paths getting into each other and some point breaking off and going to infinity. It means most likely the root locus would not go for point A. This is what's illustrated here. Okay, so we've added this pole at the origin. So you have this breakaway point here. So two paths going away. If you wanted to find actually how these two paths are going to infinity, we can of course find your apply rule number 5 to get the intercept of asymptotes and the angle of asymptotes. So you can do that. So most likely now it would not go for this previous point A, which you wanted to operate at. So if you add a pole at origin, your transient would change. See what we're saying here? Because remember the position at which you want to be operating is point A. So you don't want to change the transient. You're just interested in changing the steady state of the system. So if you wanted to maintain the transient you currently have, it means you don't want to play around with this point, because this point is giving you a particular peak time, a particular settling time. So you're happy with this, but your steady state error is not correct. So you're compensating that through the addition of an integrator, which is of a pole at origin. But in doing so, your root locus has been totally disturbed and you're no more able to be at this point. So if you wanted to maintain your transient response but still have a zero steady state error or improve steady state error, it means you would just one pole at origin is not enough. This is what we're saying here. So we know angle condition. If you wanted to validate whether this point is in the root locus or not, you can use angle condition here by linking all your poles to this point and then finding all the angles. So we've done that, and find the sum of angles. You find actually it's not equal to an odd multiple of 180 degrees. It means this point is no more the root locus. So what should you do if you want to make your root locus go for that point again? So what you need to do now, you need to add a zero. So this is the pole we've added at the origin, but you need to add now a zero, very close to the pole you just added. We understand why it's very close, and in a few minutes we do that. So what we're saying here, an ideal integral compensator, a PI controller. So this S is doing the work fine, but your transient is being disturbed. So you would also add a zero close to the pole at origin. So for example, this is what you added. You're going to add this pole here, not at the origin, as it just be cancelling itself. But this zero here should be as close as possible to this one for a simple reason here. You're adding, by adding the pole here, you've created this angle here, which is known as theta PC. So it's a compensated angle for the pole. Now you would want to add a zero so that you get a positive angle, which is almost the same as this angle. Because when you do the sum here, you want these two to cancel out so that you are at the same point you were before. So anyway, in terms of sketching of a root locus, you see clearly when you add this pole here and a zero close to it, the path from that new pole is simply going to zero if added, and then you expect the root locus not to change. This is one way to look at it. The second way to look at it is in terms of angles here. So the angle due to the pole you've added at the origin and the angle to the zero you've added close to it are almost cancelling out, because we know the angle of pole is negative and the angle of zero is positive. So these two are going to cancel out, and then you get the same angle contribution you had before, which would be an odd multiple of 180 degrees, means your root locus is going to go for that point more or less. You see that's not exactly going to go for the same point, but it's going to go very close to it. Okay. So the required gain at dominant pole is about the same as before compensation, since the ratio of the length from the compensator pole and the compensator zero is approximately equal to 1. Let's understand what this is saying now in terms of length. So this one is talking about angles. So by making these two very close together, it means the angle will be very similar, as close they are together as much as possible. As when they start getting further and further, of course, these two angles become different, and then you're changing where this point will be located. Okay, so this is the angle consideration. The second one, of course, when we found the gain, remember when we found the gain at a particular point, we took the ratio of the length of all the zeros in the numerator and the length of all the poles in the denominator. And then once we found the value of a function at this point by doing this ratio of lengths of vectors corresponding to zeros over the product of length of vectors corresponding to poles. So once we do that, then we do 1 over this value, we get the gain k. So we've seen that calculation as well. So in this case here, another way to look at this problem, why these two have to be as close as to each other as possible, is the closest these two are to each other, the length of these two vectors, which are produced, of course, one from the pole and one from the vector, would be almost equal. So if you think of the computation of that gain k, so these two lengths will cancel out. This is another way to look at it, why these two should be as close as possible to each other. Now, again, the same way we've dealt with angle, if they are very close together, then the ratio of these two vectors would be equal to 1. If not, as you start moving this 0 further and further away from the pole, then the ratio of these two will not be the same. Means you're going to change the gain k, and change the gain k means your position of your pole would not be as before. Let's take an example to illustrate this. The steady-state error has been improved without appreciably affecting the transient response. The transient response can change a bit if you have a small change of peak time, setting time. It doesn't mean a lot to change unless it is, and you'd have to again fine-tune your result. But it means we have been able to improve the steady-state error without appreciably changing the transient response. Let's take this example here where we have a plant shown by the following transfer function, and at this point here we're just using again k. So this is a typical problem we have been solving with root locus before. So this is currently your plant. You can very well see here, if you find the error of a system to step response, you're going to find error is actually non-zero because it's a type 0 system. So sketch a root locus. So you're going to put your three finite open loop poles at -1, -2, and -10, and then you can use rows to sketch it. Given that the system is operating with a damping ratio of 0.174, so it means you still want to preserve a damping ratio of 0.174, so you can draw your damping ratio line on your locus, and then you can find what's the particular point you're operating at currently. So it's going to give you a specific peak time and setting time, which you can work out. Now, determine the steady-state error of a system at a damping ratio of 0.174. So let's do that. So this is what you're getting for your root locus. Okay, and then you draw your damping ratio line 0.174, which corresponds to an angle. Once you do that, you find the intersection of your root locus with your damping ratio line. And then it means from this point we are getting now, so minus 0.694 plus J 3.926, you can work out your peak time and your settling time. This is what you said earlier. You can easily do that, and you can search along this line using, so in your lab sheets, you can have examples how to do that. You can find there are functions to do that where you can click on a point at the intersection of your root locus with the damping ratio line. So let's say we do that and you find your operating point. It's called an operating point because this is where you are going to operate to achieve the transient response you want. So once you do that, you also find the corresponding gain. So when the gain is 164.6, you get these two, and of course at this part again you're going to get a third pole as well, because we know you have a point as well here, you have a path here. So basically we're saying here we are operating at these 2 points and this one here. Now remember, we're trying to make an approximation here. So it's a third order system. We want to approximate it to a second order system. So the further this third pole here is to the left, we know if it is a very high negative value, the exponential of the high negative value is going to give you a negligible contribution. So it means the further this third pole is to the left, the better the approximation is to a second order system. So these 2 poles here would be the dominant poles of the system. Now, if you want to find a steady-state error, you find your KP limit as S tends to 0 of G of S. So we've done that, and you set your gain K as 164.6. As you set S tends to 0, you get 8.23, and then your steady-state error is 1 over 1 plus KP, so you get 0.108. So currently your error is non-zero. Now, if you wanted it to become 0, it means this is where we're adding the PI controllers here. So this was the original plot. This was your gain K here, which is set as 164.6 to achieve this point. So you're happy with this transient response. You don't want it to change appreciably. So first you add this pole at origin, which is the integrated part, but you see that's not sufficient. If you just do that, your root locus will be distorted and you won't be able to achieve this particular point here if you just place pole at origin. It's not going to go through that. So this is why we have added this 0 as well as part of a controller, as part of a compensator. So this one is making sure Locus actually go through a point as close as possible to the original one. Now we've chosen this one to be at minus 0.1. You could choose other points as we see as we go along. So this is what happens now when you place your compensator pole n0. So you have the pole at origin and the 0 at minus 0.1. You can see now your Locus have more or less the same form as before, but when you try now to plot the damping ratio line and find the point of intersection, the pole has changed a little bit and the gain as well. So there will be slight change because simply these two are not at the same point. So there will be some distortion caused. So with a new with the new Locus with the addition of a compensator now is going to have these properties as we've said. So the gain is going to 158.3 instead of 164 before. So you would need to now validate whether the new response you're getting is fine or not. Now, if you look at these two poles here, where you're operating, so minus 0.678 before you were at minus 0.694. So this part here is going to affect your settling time. So you expect your settling time to change a bit. Now, the peak time as well was rated to 3.926, this pi over 3.926. So now it's 3.837. So it's not changed appreciably. Settling time peaking would not change, and the percentage overshoot will not change at all because you are still operating along the damping ratio line. Of course, if your second order approximation is valid. So if you find Kp as expected, now you have a type 1 system. So if you find Kp, you get infinity and your steady state error is 0. So you have achieved your aim first in terms of steady state error. If you now look at the step response in terms of this transient, so this was your previous system, which was uncompensated. So you can see you had an error here of 0.108. Now the compensated system here in blue is actually obtaining as a final value of 1. So it means you don't have any steady state error, as we just calculated. Now, if you look at the transient part, you find your system, your overshoot is the same as expected because you're operating along the same damping ratio line, and you find your peak time and your settling time are more or less the same with slight change because the pole is exactly the same point, and the gain also have changed a little bit, but it's more or less the same, so that should not be a point of concern. So by simulating the system now, you can find you're validating your result, you're validating, yes, the second order approximation is working fine. So this is how you can show your results here. So you have this part K, which is the proportional part, and you have this integral part here. So when you add these two, you get your PI controller for dealing with steady state error. So if you look at this block diagram here, it means your whole compensator is K1 plus K2 over S. So you can just very easily work out K1 plus K2 over S, and then you can just make common denominator, you get a form like this. Yeah. So if you relate to what we did earlier, so we had S plus 0.1 with the particular gain in front and over S, it means you can very well work out the value of K1 and the value of K2 over K1 should be equal to 0.1 in our case, and you can work out the value of K2 from there. It means you can bring back your compensator in this form here where you have K1, which is a proportional part, and then K2 over S, which is an integral part. So you can work out values for K1 and K2 very easily. If I just go back a few slides here, you can find this is a form of your compensator as one block. So in this case, you can find your K2 over K1 is equal to 0.1, and your K in front here is what you got, 158.2. So you can very well work out the values here. So do work this out. Now, the next topic we're going to cover in the next video is lag compensation, where we are not using a pure integrator, but we're using an integrator which is not at the origin, which is very close to origin, and the main reason for that is that you get passive circuits. So we're going to have a video going to cover the lag compensator. So stop here and wait for my next video. Thank you very much.